Okay, so good day. So if recall the last video we talked about integers. Now let's extend our knowledge about numbers and talk about rational numbers. Historically, the need for a closed set for division came before the need for closure for subtraction. We need to find some number k so that 1 divided by 2 equals k. The ancient Egyptians limited their fractions by requiring the numerators to be 1. So 1/2, 1/3, 1/4. The Romans avoided fractions by the use of subunits. Feet were divided into inches and pounds into ounces, and a 12th part of the Roman unit was called an uncia. However, people soon felt the practical need to obtain greater accuracy in measurement and the theoretical need to close the number system with respect to the operation of division. If you remember the idea of closure, it's like you get two numbers from a set and the result should still be a member of the set. For example, um, the set of natural numbers is closed for addition because when you get two natural numbers, 1 and 2, when you add them, the answer is 3, and 3 is still a member of the set of natural numbers. But when it comes to division, you can't say that the natural numbers are not closed for division because 1 divided by 2 is 1/2 or zero point 0.5, and that is not a member of the set of natural numbers. So in the set of integers, some divisions are possible, right? So some divisions are closed. 10 divided by -2 is -5, and that's still a part of set of integers. However, certain others are not. For example, 1/2 or -16/5 or 5/12. If you evaluate those, you get a decimal number with a decimal, and that's not a member of the set of integers. So just as we extended the set of natural numbers by creating the concept of opposites, the positives and the negatives, we can extend the set of integers. That is, the number 5/12 is defined to be that number obtained when 5 is divided by 12. This new set, consisting of the integers as well as the quotients of integers, is called the set of rational numbers. The set of rational numbers, denoted by this fancily written letter Q, is the set of all numbers of the form a over b, where a and b are integers and b is not equal to 0. Okay. So notice that a rational number has fractional form. In arithmetic, you learn that if a number is written in the form a over b, it means a divided by b, and that a is called the numerator and b is called the denominator. Also, if a and b are both positive, a divided by b is called a proper fraction. If a is greater than b, an improper fraction if a is greater than b. So I meant less than b kanina, I'm sorry. And a whole number if b divides a. So if b divides evenly into a, then the answer is a whole number. It is assumed that you know how to perform the basic operations with fractions, but we will spend the next few pages reviewing those operations. So the fundamental properties. If the greatest common factor on the numerator and the denominator of a given fraction is 1, then we say the fraction is in lowest terms or reduced. If the greatest common factor is not 1, then divide If the greatest common factor is not 1, then divide both the numerator and denominator by this greatest common factor using the fundamental property of fractions. So what is the fundamental property of fractions? If a over b is any rational number and x is any non-zero integer, then a times x over b times x is equal to x times a over x times b is equal to a over b. That is, given some fraction that you wish to simplify, first you find the greatest common factor of the numerator and the denominator, and then use the fundamental property to simplify the fraction. For example, if we reduce the given fractions, letter A, 24 over 30, and letter B, 300 over 144, let's start with letter A. First, for letter A, we find the greatest common factor. And what we learned from our previous meetings is we can do that by using converting both numbers into the canonical form of their prime, what was this? Prime factorization. So if you want to review that, then you can refer to old notes. But 24 is equal to 2 times 2 times 2 times 3. And 30 is equal to 2 times 3 times 5. And to get a GCF, you get representatives for the primes and multiply the representatives with the least exponent. So what I mean is the GCF is 2 to the 1. So you have two choices, right? It's either 2 cubed from 24 or 2 to the 1 for 30. And you choose 2 to the 1 because it has the lowest exponent. For the prime 3, you have no choice. Both are 3 raised to the 1. And for the prime base 5, you select 5 to the 0, which is the lowest. And 2 to the 1 times 3 to the 1 times 5 to the 0 is just equal to 6. And so the GCF is 6. So what's the next step? So notice that um, 6 appears to be a factor, and indeed it is the greatest common factor for both numerator and denominator. So you now convert each numerator and denominator as the product of the greatest common factor and the remaining factors that make up the original values for the numerator and denominator. So for the numerator, we have 6 times, then there's 4 left, so 2 squared, over 6 times 5. And what happens is that you can actually cancel out 6 because it appears in both the numerator and the denominator. So what you're left with is 2 squared over 5 or 4 over 5. So this is what is known as the simplified version of your fraction. And it is equivalent to the original fraction, but in a much simpler form. Simple in the sense that this time around, the greatest common factor for your numerator and denominator is just 1. So the GCF of 4 and 5 is 1. So how about for letter B? It's 300 over 144. Again, you represent each number with a canonical representation for prime factorization. And then 300 will be equal to 2 squared times 5 to the 1. 2 squared times 3 to the 1 times 5 squared. And 144 will be equal to 2 to the 4th times 3 squared times 5 to the 0. Now to get the GCF, so for each prime base, you select representative, and your representative should be the one with the lowest exponent. So for the prime base 2, you select 2 squared from 300 because 2 squared has a lower exponent than 2 to the 4. And for base 3, you select 3 to the 1. And for base 5, you select the lowest exponent, 0, 5 to the 0. And so our GCF is 2 squared times 3 to the 1 times 5 to the 0, which happens to be equal to 12. And again, the next step is to represent 300 by the GCF times whatever remains. So 12 times 5 squared, and also 144. You represent that with 12 times what is left, which is 2 squared times 3. And now you have 25 over 12 after the 12s cancel out is the reduced form or the simplified version of the original fraction. It is reduced because, again, the GCF of the numerator and denominator is now equal to 1. Notice that the reduced fraction may be an improper fraction. Again, this is called an improper fraction because the numerator is greater than the denominator. Operations with rationals. Now that we have defined rational numbers, we need to review how to add, subtract, multiply, and divide them. The procedure for each of these operations is given in algebraic form. So there, I hope you still know how to do this. This is basic stuff from your grade school. How to add, subtract, multiply, and divide fractions. So let's try for letter A, 1/3 minus 2/5. 1/3 multiplied by 2/5. I mean, all you have to do is multiply the numerators and multiply the denominators. And the answer is 2 over 15. So again, here what you do is you multiply the numerators and then you multiply the denominators. So multiplication is very easy for fractions. Now, when you multiply a whole number in a fraction, you have to write the whole number as a fraction. So -5 is actually equal to -5 over 1. And now you will see that you have to multiply the numerators. -5 times -2 is equal to +10. And then you multiply the denominators. 1 times 3 is equal to 3. And you have an improper fraction as a result. So here you have mixed numbers. Mixed numbers are a combination of whole numbers and fractions. But in order to do this, you have to convert the mixed number as an improper fraction. So I hope you still know how to do this. 3 1/2. To convert that into a mixed, an improper fraction, you have to multiply the denominator with the whole number. So 2 times 3, and then you add the numerator. So 2 times 3 is 6. 6 plus 1 is 7. And so you have 7 over 2. You copy the denominator. And you can do the same for the second one. So 2 times 5 or 5 times 2 equals 10. 10 plus 3 is 13. So the improper fraction is 13 over 5. So copy again the denominator. Now that the fractions are in improper form, then you can just multiply the numerators and then multiply the denominators, and you will get 91 over 10. So for most complicated fractions, the best procedure is to reduce before multiplying rather than after, as illustrated here. So 3/4 by 2 times 2/3 shows that you can cancel out the 3's because a 3 appears in the numerator as well as the denominator. So they cancel out and they are left, they become 1, both become 1. And there is a 2 in the numerator and a 4 in the denominator. And 2/4 that's equivalent to 1/2. So the 2 becomes 1 and the 4 becomes 2. So you are left with a much more um, simplified fractions. So 1/2 times 1/1, and the answer is 1/2. In division, so actually division, there's a rule I hope you still remember. When you divide a fraction with another fraction, the second fraction, you can convert the division into a multiplication, but you have to reverse the location of the numerators and the denominators. So as you can see here, -3/4 divided by -4/7 is equal to multiplication of 7 divided by -4. So notice that the second fraction is reversed from -4/7 to 7/4. So that's how you multiply or you divide fractions. Then it now becomes a matter of just multiplying the numerators and multiplying the denominators. And in this case, since the negative sign appears in both numerator and denominator, you can cancel it out. And you're left with the final answer, an improper fraction, 21/16. Here, 4/3 or 4/3 divided by 8/9 is equivalent to 4/3 times 9/8. Now, again, you reverse the, or you, actually, I think the term there is to convert the second fraction into its reciprocal. So 8/9 becomes 9/8. Okay. Operations with rationals. So to carry out addition or subtraction of fractions, you must find the least common denominator, LCD. The least common denominator is the same as the least common multiple. So So the rule is that you really can't add the numerators and add the denominators. You'll come away with the wrong fraction. So you have to make sure that both or all three fractions have the same denominators. So basically, you have to convert each fraction into its equivalent so that both or all three end up having the same denominators. The way to do that is to find the least common multiple or the least common denominator of the among the denominators. And let's start with letter A, 5/24 plus 7/30. So the denominators are 24 and 30. And so we can find the LCM of these numbers again by what we learned, right? Using prime factorization, getting the LCM for both numbers is choosing the representative for each prime base, the representative with the highest exponent. So if last time we chose the lowest exponent for GCF, this time we select the highest exponent for LCM. So for prime base 2, the highest exponent is 3, so 2 cubed, and we select 2 cubed. And for base 3, the highest is 1. You have no choice. Both are 3 to the 1. And for base 5, the highest exponent is 1. So 5 to the 1. And it turns out the least common multiple for 24 and 30 is 120. And this is also our least common denominator. So since our least common denominator is 120, so how did we go from 24 to 120? We multiplied 24 by 5, right? So 24 by 5 is, okay, so since we had to multiply 24 by 5 to get 120, we also have to multiply the numerator by 5. So that helps keep our original fraction the same. So 5 over 24 becomes 25 over 120. And how about for the second fraction, 7 over 30? How did we convert 30 into 120? Well, we multiplied that by 4. And so since we multiply the denominator by 4, we should also multiply the numerator by 4. So 7 over 30 becomes 7 times 4 over 30 times 4, which is 28 over 120. So now we have two fractions which actually equivalent to the original, except now this time both fractions have the same denominators. So what we can do now is simply add the numerators and then copy the denominators. So 25 over 120 plus 28 over 120 gives us 53 over 120. So, right. Yeah, basically, if you want to review these, you do have access to this PowerPoint presentation. You can check that out in the like in your Blackboard course, and you can see the other examples there. So those are the rules for the operations of rational numbers. Probably a topic you are already familiar with, but it's well worth reviewing. Thank you very much. Goodbye.